Hi. Yeah, so I'm going to talk about work we've been doing at Web3 Research that's not yet in Substrate, but will be in Substrate at some point soon, at which point... Louder? At which point you will all be able to use it to do cool stuff. I've been working with a few people in the research team, Alana, who's doing the proofs, and Sergey, who did the code, and also with Fatima, who's here. And those are on the paper, and Syed over there is also helping implementing BLS. But we'll get to that. Okay, so what am I talking about here? Light clients. Probably everyone here knows what a light client is, right? It's software we want to follow blockchain consensus and get data from the blockchain, but we want to do it on a resource-constrained device. And we have our consensus system with hundreds to thousands of or more validators, and they go and agree on something. In Polkadot by say Grandpa, and we want to convince a thing on a browser, a thing in the browser on your phone. Now you might first be thinking like small dot here, but there are other applications. Anyway, so the difficulty of a light client compared to a full node is the light client's not, full node is connected to the peer-to-peer network that defines, your blockchain. It's listening to all the consensus messages. It's importing all the blocks as they come. But a light client, on the other hand, is not. It might not. It's not connected to your network. Maybe it's only talking to a single full node, a single centralized server who we shouldn't really trust. It's not interested in everything. It doesn't want to download the entirety of the data and the entirety of the state of your system. It's not interested in things going on with all blocks. We wouldn't want it to be interested in all headers of the chain. Just ones where stuff happens that's interesting to it. But we still need to follow the consensus, because what we agree upon in Polkadot is sort of determined by what the validators decide, and the validator set keeps changing. And this is actually the thing that makes it a bit awkward. Now, you might be thinking of sort of small dot here as a light client, but the truth is that this sort of connection pattern occurs in other places. If I want to sync a full node fast, we have this warp sync protocol, and we want to sync a newly booted node from Genesis. And basically the way you do that is you sync as if you were a light client, and then only when you've sort of caught up to recently do you get the state of some checkpoint, and then start following it like a full node. Another obvious sort of application is on-chain. So if we have a bridge, a bridge needs to know what's going on another chain. So the way you do that is basically you put a light client on chain. Of course, as you guys probably know, on chain is like actually the most resource-constrained environment of them all. It's way easier to get something working in a browser on my phone than it is on a blockchain. Where data and everything becomes really expensive. And yeah, also security is a bit critical on bridges as well. So now we've seen, I'm sure anyone who's following the news just hears every day about a new bridge that's been hacked. So when I last looked into this, it had been 1.2 billion. That was back in August. Since then, I've stopped counting. I don't know if anyone else is. But yeah, there's billions that get stolen from bridges. They represent a large thing of every sort of hack there is. Most of them. And it's super important that an on-chain light client is following consensus securely. And this is difficult, right? Because it's so resource constrained. People have this resource constrained situation. They have to cut corners. How do we do this? Maybe we do some optimism. We claim something and someone challenges it later. And the problem with this is it's not necessarily secure. So who here remembers FOMO 3D? Any hands? Yeah, a few. Those who don't know about it, you should look it up, right? It turns out that even Ethereum is censorable if you pay enough money, and this has been done in practice. So, and this is a concern if I want to put a claim of something and then have it being challenged, right? Oh, and this is a picture of a rainbow I took on Sunday from the castle near here, right? Some of our fun. Anyway, moving on. So the thing is here is we need to follow the consensus of 1,000 guys in this sort of rapidly changing, well, okay, maybe not rapidly, maybe once every day. It's an era on Polkadot, right, that we do a little election, but actually once every session we can maybe change some keys. And sessions are, what, 6 hours on Polkadot? So once every 6 hours, we have to change our validator set. And if you sort of think about so the way it works now is every session that there's a header that gives the session keys of the validator set for the next session. And in Grandpa, these guys come off and sign up on that. And what that means is we have a Grandpa justification with 1,000 signatures, or well, on Kusama, maybe 700 on Polkadot. Maybe 200 signatures we can get it down to on Polkadot. But we also have the 300 public keys, but not just the Grandpa public keys, but all the public keys in the the digest of the header. And this is where all the data. If you're trying to sync the chain from the beginning, this is where the majority of your data is. Even if you're trying to sync from a checkpoint, this is the limiting factor. And once you've synced, we can give you some state proofs. They're a lot smaller. So how would we? So we believe things if we know the validator set, we believe things the validator set has signed, like 2/3 of them are signed. So at the moment we're using boring schnorr signatures, but we could be doing something more funky. So you can use like multi-signature schemes. So Ethereum 2 now have a very successful deployment of BLS signatures. They use aggregation. They have hundreds and thousands of validators, way more than we do. But with BLS signature aggregation, they can put like one signature from 100,000 guys in their blocks. You still have to keep track of who signed it, and just importantly, you still need all these public keys, and they themselves are a load of data. Now, you could use threshold signatures, which are like more magic. With a threshold signature, you have one public key and one signature. But this one public key has to have there is a private key corresponding to this public key, but no one can know it, right? And you sort of have to share this secret among all these guys. And we need this sort of distributed key generation protocol to get it to them. And this involves everyone talking to everyone else. And it's complicated, and it doesn't really scale well to lots of people. So we can't really do that with our 1,000 guys. And even if we could, it then has a disadvantage that you get the same signature whichever subset signs. We don't know who signed what. who signed off on this. And we kind of like that. So we really like, and this is why, say, Ethereum has stuck with the first scheme. And sort of, yeah, let's think how big these are. So like one of these sort of Schnorr signatures, one of these Schnorr public keys, ECDSA, ED 25519, SecP 256K1, all these things are sort of 256-bit public keys. You also have like 256-bit signatures. And in BLS, well, if you want to be secure, you need to make the keys a bit bigger. These 384 bits. And like if it's 1,000, well, yeah, we're talking tens of kilobytes. If you're in an Ethereum situation, it's megabytes for your hundreds of thousands. Compared to that, yeah, Schnorr signature's also 256 bits. So like you're looking at maybe 6 kilobytes plus all the other stuff in the grand part justification that you'd have to do every block. And every session change, you need all these sort of 30 kilobytes on Kusama, a bit less on Polkadot, but we're hoping to get to Kusama this sort of many public keys. And the session keys in the header are a lot bigger than this because we have several public keys. So we don't really want to do any headers, really, when we're syncing. But we can't really currently get around all these public keys. And this is what the scheme that I'm going to talk to you about gets around. This is the problem it gets around. The data from these public keys. And the way it kind of works is we commit to the public key, to a list of public keys. I get this small commitment. I still want to know who signed it, so we create this sort of bit vector of who signed it. So we need 1 bit per signer, but that's a lot better than 384 bits per signer for having all these public keys, or 256 bits per signature. 1 bit, that's much better. And basically, we have the advantages of an aggregatable signature scheme in terms of the signature size, in terms of we know who signed it, and these guys not having to talk to each other to create the signature. But we use a lot less data. And so basically we build this on top of BLS aggregation. Here's a picture to explain that a bit in a bit more detail. So it's like, I have a block whose header says that this is the validator set. These are the 1,000 public keys on Kusama. These are the 1,000 public keys. And this is a later block. Maybe like these guys signed off on its header or something else. And we have this list of signatures corresponding to some of these guys. Now, so if you're using BLS on this, you add all your signatures together to get the aggregate signature. You add the public keys of the subset that signed this, for which you have signatures. You turn those into an aggregate public key, and then you verify these two against each other and the message. That's how BLS works. But here, we don't want to have this list. So what we're going to do is we're going to create a much smaller commitment to this list. And we're going to give the a bit vector here, which is 1 when this guy signed it, 0 when they didn't, and we're going to prove from the commitment and this bit vector that this is the aggregate public key, and we create a SNARK to do that, which I will talk about next. And so now our proof is this commitment, the aggregate public key, the aggregate signature, the bit vector, and the SNARK. And the SNARK tells us that, yeah, this aggregate public key is correct, and then we can use the aggregate public key and the aggregate signature in BLS verification. And now we know that this many guys signed it. And if we know what this commitment corresponds to, we know exactly what their public keys are. If we don't, it's kind of meaningless. Now, yeah. Okay. So we need a SNARK, and SNARKs are magic. But this is Build a Room B, right? Can I try and explain this to you guys? Yeah, okay. So if you don't want that, like I've got 4 slides. I promise you, there's going to be moon maths for the next 4 slides, when I'm going to give you a peek behind the curtain, and then we're going to go. Then I'm going to give you some benchmarks. We can back down to earth with real world data. So how does this work? How do we? So what we need to do is we need to prove that we have some bit vector. We need to prove we have sort of this list of public keys, and we need to prove we need to add up the public keys where the bit vector is 1, and say something about the total. So this is elliptic curve addition, which is a bit weird, but there's a formula for it. You can go and look it up. I want to verify, that if B is 1, that this thing is this thing plus this thing. Otherwise, these 2 things are just equal. I can write this in terms of polynomials. Maths. This is maths. It's modular maths over some prime field. But the fortunate thing is that elliptic curve cryptography is like elliptic curves are modular math over prime fields, and this is exactly what you can do inside a SNARK, which is helpful. So what am I trying to compute? The sum of public keys. So we have we consider this sort of a table. This will be the x coordinates of your public key. This will be the y coordinates of the public keys. This vector indicates some bits, and we want to add up these guys where these bits are 1. We add 2 extra columns, which are accumulators, which will be the sum of the public keys so far. And these 2 things in the I plus first column have got to be this thing plus this thing if this is 1, or just this thing if this is 0. Now, on the previous, so these things I've highlighted, these sort of cells of this table, they should be satisfying the polynomial relation I had in the previous slide. And I can turn this into a complicated system of polynomial equations. The way I do that is with the entries in these columns, I do some interpolation. A Lagrangian interpolation, I can create a polynomial which has these things at certain these values at certain points. And that gives me an incredibly complicated system of polynomials. You don't need to read this. And if I just verify these equations hold, our inputs being this public key here, then I'm sorted. The way SNARKs work is I can test that this system hold if I can test this at a random point. These are polynomials, they're functions. I can test them at a random point, and then we have this cryptographic craziness called a polynomial commitment scheme that I can commit to these polynomials and convince you that this is the value at a certain point without giving you the polynomials. And with that magic, you can create a SNARK. Now, there was one minor issue with the simple way. This was the simple way. There was one minor issue, which is dealing with this bit vector. So we have this polynomial that we have to interpolate from these points, and everything else is sort of constant time except this part. And in this part, it's like if I take each of these things as a single field element, each bit is a single field element, then I need to do as many field operations as there are bits to interpolate this polynomial, which I then put in the thing in this massive set of equations. That's fine as long as I've only got 1,000 validators, it turns out. But when I have more, it's like we have to cut this up differently. It turns out we can actually fit 256 bits into a field element. And if we do that, then we end up doing way less field operations, addition and multiplications of these things. But we had to make the scheme a bit more complicated to do that. The alternative is to fully sort of snarkify it. We don't give the bit vector at all. I just tell you how many guys signed. That's a bit more like the threshold thing. And that everything is constant if you do that. And so here are the benchmarks. Now, this basic scheme, the one that I explained, that I gave in full detail, for 1,000 validators, we can get sort of 1.1 kilobyte truth, verify it in 27 milliseconds. That's pretty good. But the thing that makes this, the thing you're not going to get if you compile your thing to ZK EVM and put it in Groth16 or whatever they do these days, you're not going to get a prover time of half a second. This thing is fast enough that I can keep up with the consensus in real time, right? As soon as Grandpa, or Beefy in this case, or as soon as the validators agree on something, we can get a proof very fast. I can have a relay node that just generates proofs for blocks as they come and tells that to people. And if we scale up the validator set, we can still kind of do this. 65,000 and like even 1 million validators, Ethereum we're aiming for. Maybe one day we'll have this, but Ethereum 2 is very close to be here already. Prover time goes up a bit, even, yeah. Now the size is a lot if we have to give these 1 million bits. That's why these are 100 kilobytes. And this basic scheme, which it gets a bit slow, but never mind, these other schemes are fast. But the prover time, it's like we're talking 5, 6, 7 minutes. But in Ethereum 2, like in order to make these guys agree, they spend a lot longer. They have epochs. They get finality only once every epoch, and they have 64 blocks or something. Was it longer? Anyway, this is also real time. And this wasn't on a terribly fast machine. It's like you can probably run this half a second is going to be way slower on a high power. You can run it on a validator, and it wouldn't affect your service on anything else. So yeah, I'm claiming this is fast. Why is this fast? The reason is because the circuit is dead simple. You can't get simpler than this. I know maybe it looks complicated, but it's simple. It just does a few operations per public key to add these things together, and it's all in the modular arithmetic, the right modular, the right prime to make it work. The other reason it's fast is inside the circuit itself, we don't sort of uncommit our commitment, because our commitment is the same sort of polynomial commitment that we made the SNARKs out of. If you try to, we could hash all the public keys together, and we could prove inside the SNARK that this is the hash of all these public keys. But that will be way more complicated, like 300 times more complicated, even with a ZK-friendly hash function. That's not. People do this. Telos Pluma protocol does this, and they're way slower. Right, this is a kind of hand-optimized custom SNARK. Right. It would have been slower if you used Groth16 or Plonk or whatever your favorite thing is. One of the things I want to say is I know everyone here likes the idea. You wouldn't be here if you didn't like the idea of putting complex state machines on a blockchain, right? Probably it would appeal to you to put complex state machines inside a SNARK, a zero-knowledge proof. Like, and there's projects, there's ZK EVM, ZK WASM, that do this. But they're really slow. And the reason for it is because they're just not optimized for this architecture. It's like you have WASM, and it was optimized to do binary stuff. You compile it to this, it's something that's supposed to be low level, but it's not low level in this system. It's really high level. And so the way you have to think about it is that we're not there yet with this technology. It's kind of in the sort of 60s to 80s era of computation. Like, the high-level languages existed. They weren't as nice as the ones you guys are using, but they existed. But if you wanted to be fast, you've got to get into assembler, and you've got to optimize for the architecture. This is where we are with ZK SNARKs. You want to be fast, you've got to do hand optimization in these weird arithmetic circuits things. Avoid binary operations and other stuff you might be used to. But if you do that, we can be fast, and we can be fast enough for this application. there were some downsides to going this custom route. It made, we had to do the proof that this thing worked ourselves. Amanda did a good job of that. We have a paper, prove that everything works, and yeah, that was a lot more complicated than if we just use Polkadot 16 with some, yeah. So, okay, let's go back to what we're using this for. So basically, we have this sort of committee key, we call it, which is a commitment to the list of public keys. And we have a scheme that can verify from this much less data, just a bit per validator, who signed this thing. And now we can use that to make the session handover things much smaller. And this is going to make like clients more data efficient, whether they're on chain, whether they're in a browser. And so the next question is can we go further in how small we make something? Well, the answer is yes, we can go a lot further. But, so like Dfinity and Mina both have things with a constant size. Dfinity does this threshold, nice reflareable threshold signature scheme. Mina does, we roll up the entire blockchain in recursive SNARK. Even validity, not just consensus, but validity. It's amazing stuff. But there's sort of a complexity overhead going on here, and more. And so Dfinity's case, so like I said, with a threshold signature, the problem is the setup is complicated. Dfinity's thing is particularly complicated, and it restricts the number of validators. Likewise with Mina, in order to get recursive SNARKs, this requires complex provers. It also requires you to simplify your logic in the most, you need to really simplify your logic to fit it in these SNARKs. And, this means that they can't do what we can do on Substrate when they're rolling up the validity of the chain. And even for consensus, they have to simplify all over the place. And they're still doing longest chain, which actually isn't great for light clients. Now, someone who's taking an approach which we basically based ours on is Celo's Plumo protocol. They're using the same curves as us. They're using BLS. And they're rolling up 100 validator changes, which is amazing. But they're only doing it with 100 validators, and we have more, so they would get less for us. And their thing takes hours on a fast computer to generate the SNARK, compared to our half a second, which is, a slight difference. But they're aiming for something different. But there is a sort of problem with all of these schemes compared to ours. It's going to be particularly important when it comes to bridges. And that is, with this data, we lose information about who signed anything. Right? If we see a proof that says something that didn't happen, we not only don't know who signed it, we don't know when they signed it, right? If we just have the same key and we keep it forever and it's reshared among these guys, we know that 2/3 of people at some point signed this thing. We don't know which 2/3, we don't know when. Mina, likewise, no information. And Celo, you get it down to 100 errors. Great, but we don't know who signed this stuff. And what we're interested in is this idea of accountability. And what that means here practically is that if we see this light client proof and the chain goes off and decides something different, then if we have both of these things together, we can decide who is responsible and we can slash them. And we care about this. So like some of the security of Polkadot comes from the ability to slash validators. Now, most of the time, 2/3 honesty is fine. And to be honest, if I'm just trying to check my balance on my wallet, I'm fine trusting 2/3 of validators. It's a lot better than just trusting Emperor, right? But if I have a bridge that billions could be stolen from, now I'd really like not to trust these guys anymore. We'd like to assume that our stakers are rational instead. And to do that, we have to slash these guys who misbehave. But there is one big advantage of a bridge, which is, these guys are proving to the bridge that something's happened, but they're posting this on a public blockchain, right? So we're going to know forever, this data is going to be there forever, and if they mislead this chain, then we can just take this data, we can post it on the original chain, and it can figure out who is responsible and slash people. And now we basically have the same security for this bridge as we have for the relay chain in the first place, right? You can't get more secure than this, you know, more secure than the original chain. So this is as good. This is as good as it gets. This is like perfect for bridge security. Of course, there are downsides. We have to use this particular crypto. You won't get this working on Ethereum until, you know, in 10 years when they accept the EIPs that are already there to put this in. But substrate, we can probably do this. I suppose that, yeah, the question is when. Well, okay, so we have code for the prover and verifier for this SNARK scheme. That's in a repo. Sergey did this. It's kind of ready to go. We proved it works. We have a paper. But we're sort of waiting on BLS to go into substrate. Syed over there in the tartan is, he had this pull request, but then no one commented on it, and it got closed due to inactivity. But he's still working on this. And in particular, working on integrating it into Beefy. Our finality, our post-grandpa finality, you know, another layer of gadget that we're using to, we did for the Ethereum bridge, but probably all light clients and bridges are going to use this because it's nicer than grandpa. We have everyone sign the same thing. We can do it with different crypto, currently SecP for use on Ethereum, but we're going to do it with BLS as well. Now, the next step after that is we need to get an off-chain worker to generate these proofs. And then you can run a relay to generate it, or anyone can run a thing to generate these proofs and start serving them to light clients. After that, we'll want an on-chain verifier, and then we can put it in a bridge. You know, at least a substrate bridge where we have both sides. Sort of, that's the goal. Yeah, so I didn't have a link to the paper. That should have been here. It's on ePrint. You can probably look it up from the authors. Yeah, what do we do with this? So as I say, that we were targeting bridges for which this security is super important, but it is going to make everything else, you know, use less data. So if I'm using, you know, if we get this working in small dot, then you can use it in, you know, in a browser extension on a phone or whatever, and it will take less data to sync the chain than it does right now. And we'll be able to do stuff like sync from Genesis. So right now we're only syncing from a checkpoint, which you trust. Now we'll be able to sync from Genesis. You still want the checkpoint because it protects you from long-range attacks, but we can verify this checkpoint and not just trust parity to tell us where we should start verifying from. Yeah, that's where we're at. So this is actually a really simple scheme. It has the advantage that compared to all this complex stuff like distributed key generation, it's way easy to just bolt on top of your existing protocol. Like, we already have this. We don't want to touch our consensus, and we can still have this. And, yeah, I just want to say all this SNARK stuff, hand optimization is still the way forward for now, especially if you want to be really fast, and we wanted it not to, you know, we wanted to get lifetime proofs fast. You know, not much slower than we get finality. And to point out, yeah, we don't have to abandon accountability to get a light client. It's super important for chains. We have code. This is real. Go and check it out. Do we have time? Okay. Yeah. Excellent. Hey.
Hello? Okay, awesome.
Hi.
So I had a few questions about the custom SNARK.
Yep.
Does it have a trusted setup?
Right. Okay, so we're using KZG, the KZG commitment scheme. It has a trusted setup, but it's universal. And what that means is that we can use Plumo's trusted setup for our thing, or we can use it's updatable. So we can start with Plumo's thing. We can do a few updates, maybe get a few extra community members or whatever involved, and then we can use it. So it's the nice kind of trusted setup.
Have you measured how fast and how big the verifier will be in WASM, or is the idea to add host functions?
Right. That's a bit of another discussion. It should be fast enough that you can do this in a block in WASM. But we have a plan to use the library that this code depends on. We're going to integrate it into Substrate, and we'll be able to, accelerate certain things with host calls. That's an ongoing plan. Like, first step, we implement it in WASM, and then we, when the host calls are there, we'll be able to use them. Because it'll be the same library and both in Rust, the same data structures.
When you show the prover times and stuff,
yes.
Here. So you lose the accountability in the counting scheme, right?
Yeah, the counting scheme doesn't have accountability.
Yeah, okay.
But obviously, it's going to be, they're always reasonably fast to verify.
Yeah, it's
actually,
about the size.
It's slightly bigger on the small end, but on the top end, it's obviously way bigger, way smaller.
Way smaller, yeah. But you lose the accountability, so you cannot
slash. But you lose the
slash.
accountability, so you can't slash. And it's still useful
Yeah.
to have threshold signatures without the setup, basically.
Exactly. Yeah.
But we don't want to use it for bridges. Yeah.
Yeah. Cool.
Awesome talk. Thank you. You said we will have to wait for either to implement EIPs and push them in, but like they won't do it like themselves. Like, do we have some working group that is working on pushing these EIPs and implementing them in their clients?
Oh, the EIPs. Oh, Ethereum's the whole. Like, they don't have the BLS they have in consensus in the EVM yet. So I don't know if we can realistically expect this ever to happen. I think the only one way this is going to happen, and that's if we convince them to use it, right? It actually works pretty well with 1 million signers. So maybe we can convince them to use it, but even the stuff they use is slow to get in the EVM. So that just means it'll get there eventually.
The point is that somebody has to implement it to actually get some traction. Like, if it's not in the client, like,
Yeah, no, I mean, we'll implement it. We'll prove it works. Yeah. And I should definitely, So there's a reason we did that. We have 1,000, we have numbers for 1 million, and that's because they should use it too. Their like client uses the sync committee, which is 1,000 random people. That's not accountable. And it's also too much data. Like, we didn't want to bridge to Ethereum. We didn't want to keep track of 1,000 public keys. Their like client is both too much data and not accountable.
Here in this slide, how is the packed accountable was supposed to be faster, no? But because it has much less equations.
It has extra equations. So it's a constant amount extra proof size and extra cost compared to the basic scheme, but the bit that's really slow when you have lots of signers is fast. So this actually has prover time proportional to the number of signers, but the constant is so low you don't even see the difference between this and counting at 1 million.
The verifier is that one.
Yeah.
And how come the prover of the adder is slow?
How come the
last counting that you add all the bits together, but your prover time against it?
Don't pay attention to these numbers. They're noise. Up here, you can see that the basic scheme has a faster prover time. These schemes, you have more polynomials to commit. They're more expensive.
But for verifiers,
but verifying, it doesn't make any sense with the no numbers.